It should be recording. Oh, I have my sound off. Okay. It's all good. All right. Anyway, what is a logarithm? So it's simply kind of a way of rewriting an exponential function. It's an inverse. Okay, does that make sense? It's the inverse of an exponential function. So if you have 2 cubed equals 8, you can rewrite it like this. Why do we care to do that? That's if you want to isolate the exponent. If you want to get the 3 by itself. So we use logarithms to isolate exponents, because sometimes exponent's an unknown, and we need to figure out what that is. So a great example, what if I have 2 to the x equals like 9? I know x is more than 3, because 2 cubed is 8. I know x is less than 4, because 2 to 4 is 16. Do I know what x is accurately to like 3 decimal places? No, because I'm not a human calculator. I'm just a human. So I'm sure it's like 2.1, 2.2. I don't know. I have to work it out. But how would you work it out? What would you do? You'd say x equals what?
On base 2 of 9.
Perfect. And we have fancy calculators that will do that for us, right? I can just plug it into a calculator. Actually, I got the calculator all queued up here. Lucky me. So you guys know how to locate the log in the calculator? Yeah, we do matrices here in the other class. You put alpha window, option 5. You can locate it like that. And there you go.
You do log 9 divided by log 2.
You could do that. You could do log 9 divided by log 2 as well. That's called change of base formula. Yeah, so back in the day when I was in high school, we didn't have these fancy operating systems for the calculator. I did have like the TI, it was like a TI 81 or something. I can't remember what it was called back then. It was not as fancy as this one. But that works also. You use a change base formula. Or you can take the log of both sides. Is that what you're trying to do, William? And then isolating x. Yeah, that's another technique as well. You can use log properties. Take the log of both sides and move the x to the front. Same thing, exactly. Same thing. And that's something called the change of base formula. Back in the day, I think I have it here, maybe I had it at home, I don't know. But when my dad did this like many years ago, or maybe your grandparents, because your parents are probably the same age as me, but your grandparents, when they probably took this stuff, there's something called a slide rule, where it's actually like a ruler, and you actually had to like slide to like log 9 and see what log 9 was as a decimal, and see what log 2 was, and actually divide those two decimals. So you didn't have these fancy calculators. They had like a table of log values that you had to look up, but use like a ruler to kind of like have it all there. It's kind of a weird, archaic. It's like an abacus, if you want to think like that for counting. Hopefully you guys know what abacus is, right? Good. All right, you guys. I was gonna tell Mr. Hunter, your world history teacher, if you know what that was. Anyway, yeah. So that's just the old school way of doing it. You could do it that way as well. Ollie, go ahead.
I hate to find that log base 2 of 9 like without using a calculator. But not really.
Well, no, you do log 9 over log 2. You need given log values.
Yeah.
I mean, yeah, maybe there might be another technique or algorithm that I'm not too aware of. I don't know. We're not gonna worry about that. So, all right, so let's move on, guys. I don't want to ruminate too long on this stuff. So we keep going. So let's rewrite these as logarithmic forms, and then we'll go back the other way, and then we'll do some properties of logs. Okay, so you'd write this as log base 3 of root 3 equals 1/2. Do you guys see what I just did? I have a power, right? Remember, power is the entire left side of this equation here. A power includes the base and the exponent. So some people say, oh, it's 3 raised to 1/2 power. Yes, of course. But they call the 1/2 the power, or maybe the 3 the power. No, the whole embodiment is a power. The 3 itself is a base, because it's like the basement, it's like the foundation of the expression, the one half is an exponent that's being raised to that, right? And what do? You make the 3 the base of your log, you make the 1/2 now the output, because you're isolating the exponent, and the root 3, which was the output in the original equation, now becomes the input of the log equation. Hence, it's the inputs, right? The input is 1/2, the output is root 3. Now the input's root 3, the output's 1/2. Make sense? Right? That's the output. Sorry, that's the input, root 3, that's 1/2. Because 3 raised to that power equals root 3. We know 3 and 1/2 is root 3. We know that. Let's do this 4 more times. Right? So you're gonna write log base 7 of 7. I'll put that in parentheses, by the way, make life a little easier. Equals 1. Log base 3 of 8 equals x. Log base 4 of 1 equals 0. Log base 5 of 1/25 equals what? -2. Now, if I go the other way, how do I write the reverse? 16 equals what? Yeah, that's pretty easy. Yep. Or 1/27 equals what? 3 -3. Okay. All good? Yep. Okay. Properties, pretty easy stuff. That's going to equal 0. Why? Because 1 equals b to the 0 power. So of course that's 0. This equals 1. Why? Because b equals b to the 1 power. That equals 1. So whenever
Why is the first one understand?
why is the second one 1?
First one.
Because b to the 0 power is 1.
Anything to zero.
Anything to the 0 power is 1, right? Right? We good with that?
Yes.
Yeah, whenever you have 1 as your input for a log, the output's always 0. Always. Whenever the input is the same value as the base of the log, the output's always 1. Always 1. So for example, if I give you some really crazy here, that's still 1, right? Who cares? Still the same thing. Because 1.683 raised to the 1 power is still 1.683. Okay. Some more here. Ask me why. That's because b to the y equals b to the y. So that'd be x. This would be x. That's because log base b of x. Let me switch colors for a little bit. Contrast. Because I'm making that x pink. So that's just 14. Okay. All's good? No questions? All right. Good. All right. Let's move on. All right. So if we evaluate, yes, go ahead. No problem. Right here. Okay. And it's kind of tricky with the way things fit, right? So what's happening here is let me do this actually. This is a then we like some colors. Okay. Let's do an equal sign. We'll need a apps. All right. So let's make this B blue. Let's make that green. And let's make that we'll call this Y. Okay, so this whole embodiment will call Y. All right. So we know this, right? We have B to the x power equals Y. It's the same thing as saying you agree about that, right? Okay. So what's going to happen now is that this Y is going to join that new B. It's going to look like this. So what does y equal here? X. And what's this whole thing equal to? Y. So if y equals x, then this whole thing has to be x. Does that make sense? Yeah, the way things have shifted, because this shifted down, that jumped over, and that jumped over. And what's in y's position now? X. And what is y equal? This whole thing. That's what this whole thing is just x. You don't cancel, don't do that. It's not division multiplication. Are they inverses? Yes. You're putting a log inside an exponential function. Why would we put an inverse into itself? It undoes it. Because the undoing process, that's what it does. That's what's happening. But mechanically, if you're being a color coding like this way, that moves over here, that moves over here, that moves down. Oh yeah, y is in place of x. And hoping it's y, that's why it's x. So if I were to give you something really strange here, let's say I did so Clay, see what I'm doing here? Yeah, from Squid Game. Okay. You know I was gonna sneak that in. So who cares what number I choose? It's X. So can't wait for season 3 to come out. All right. Actually, my next show coming up, everyone watch White Lotus. That is so good. It is like this place, by the way. There's like characters from not you guys, but like from like 10. Well, no, it hasn't come. The third season come out yet. No, I've already. No, when it came out, I binge watched it. I don't know actually. So my wife didn't watch season 1. I watched it by myself. We watched season 2 together, and then we went back to watch season 1, which is kind of interesting because then you start noticing all the different characters and how they play a role and see like the guys, like the woman's husband, like how. I'm not spoiling too much. But anyway, if you go back like 10, 15 years ago to school, there's certain like characters in that show that are like students or families at this place. Oh yeah. Oh yeah. Like that. I would say that's like that person, that's like that person. I talked to employees at the school. They're like, oh yeah, that's totally that. It's so yes, there are a lot of parallels to like affluence, 100%. So not you guys. You guys are nice people. You guys are good people. Right. But yeah, it's pretty funny. Okay, I digress. Let's do this. All right. You guys see US 2? Okay. Do you guys see why this is 2/3? Why is that 2/3?
Square, and then you take it.
Good. This one would be hold on. 1/2.
And then 4. There's 4.
Oh yeah, duh. Yeah, of course, it's 4.
Oh,
Yeah.
I was like,
Yeah, because 3 squared equals 3 to 1. Yeah, right, you're right. Yep. Yeah, if you're ever stuck, we could do 9 equals √3 to the x. So 3 squared.
gotta go. Keep on doing that.
So x have to be 4 in this case. So you could look like that. And that one would be -1. Yeah, -1. Okay. Now, 2 special types of logarithms, common logs and natural. Common logs have base 10, natural logs have base e. Usually, if you have base 10, you just don't write the base. So the assumption, the default would be, if you don't see a base, assume it's 10. Here you write ln. Sometimes I do like to write log base c when I'm trying to undo it. Especially when we move on to calculus, because we won't do derivatives of this type of stuff. I'll have to kind of deconstruct ln in that way. So this should be pretty easy. That's 2. What's this one going to be? Good. That one's 1. That's pretty obvious because the base and input are the same. That one's base 10, but raised to what power? 1/5. Yeah. Cool. All's good. All right. Oh, it's more. Okay. Pretty simple. That should be 2, 0, x, y, x, and 1/2. Once you get the hang of it, you just go pretty fast, right? But, because the log of e is undo, so you get 2 log 1, any log of 1 is 0. These undo, that's x. These undo, that's x, because the bases are the same here. Bases are the same, that's y. That's e to the 1/2 power, bases are the same, you'll.
Being the natural, like e raised to the natural log is just one.
Yeah, wait, e raised. Oh, right. Well, e raised to the natural log of what? What's going to happen is that these undo each other. So you're stuck with this. No, it's x.
Right, one.
Equals x. No, this would equal 1. Okay, what if I had this here? Then that's 1. Because what's ln of 1? 0. What's e to the 0? 1. Or these undo each other, leave me with this. Does that make sense? Actually, that kind of helps understand why why that would be the final answer, right? Because natural log of 1 is 0, e to the 0 is 1. So whenever you see this here, the bases are the same, both the power and the log, then there's an undoing, and you just get whatever is right there. Try to go.
Is there ever a situation where you could have like 2 answers to say like the rational and the
What are my 2
like,
answers?
like say the rational exponent and the root exponent like have the same answer.
What are you talking about?
Like
No, I'm trying to understand your question. I don't understand the question.
say like take log like 0.43.
Okay.
It's like so there's obviously going to be like a negative
Yeah, number. Yeah, sure. Right.
There'll also be like to that as well.
No, because if you raise e to a fraction exponent, right? Let's say I say I take the 10th root of it. It's still gonna be a number larger than 1.
Well,
right? No way can it be less than 1, because if
what
you
if the base is like
less than 1, then sure, yeah, then that's a different story. But if you do a negative of a number less than 1, then it becomes a number greater than 1. They're going the other direction. Yeah, no, that will never happen. I understand what you're talking about now. Now I understand the question, because you're trying to make things smaller. I get it, but there's different behaviors when numbers are larger than 1 and less than 1, because the growth and decay situation, right? It kind of comes back to that. If we use a calculator, I know you guys can do this. It's not hard. We'll just get it out of the way. Log 34.5. You don't have to close parentheses. Log 0.43. Natural log of 23.5. Natural log of 0.48. So 1.54. We'll go 2 decimal places. Negative 0.37. 3.16. Negative 0.73. Yeah. Alpha zoom. Sorry, alpha window. Yep. Option 5. Or hit the math button and go down to, I think, option A. Yep. Yep, there you go. This here is going to be x equals 10 cubed. X is 1,000th. Here, x equals e to the 4. And you can leave it like that. Because e itself is irrational number, so we don't have to approximate it. Just leave it like that. Okay, good so far? Okay, let's keep moving. Graphing, not hard at all. If I graph that, let's plug in 1, 0, -1. You get e, 1, and 1 over e. So e is roughly what again?
2.7.
Yeah, 2.718. Actually, this Friday is Oilers Day.
What?
February 7th.
Oh, 2.7.
2-7, yeah.
What's that egg called? Oilers?
It's not really called anything.
I think.
Yeah, good point.
Friday's more fun. So that's that graph, right? Okay, if I want to do the inverse, let's switch colors. How do you do the inverse? What do you do to the columns? Swap them 100%. E1, 1, 0, 1 over E -1. So E is 2.718, 1, 1,0. And it's symmetric about what line? Yep. Always going to mirror images about y equals x. Yeah, the inverse is right. So when you graph it, what do you notice when you graph both function and inverse? It's a symmetric or reflective. It's probably a better way of saying it. Yeah, reflect about y equals x. So that's how you graph log. By the way, we'll have a vertical asymptote. The domain range switch. Now the domain's limited. Now the range is all real. And the asymptote's vertical, not horizontal. So it's all just reversed. So we see that over here down below. And that's a natural logarithmic function. Let's fill in the blanks. Now let's do more graphs. Then we could generalize down below. So the domain was x is bigger than 0, or yeah, we'll do that. Local extrema, there are none. There's a vertical asymptote x equals 0.
This for
Log.
natural log.
It's all logs, really. They're not transformed. Continuous on its actually on its domain, which is from 0 to infinity. Increasing everywhere on its domain. No symmetry. You can't log negative numbers. Remember, x equals e to the y.
Oh, right.
I can't raise e to some power, make it negative. E is a positive number. It's just impossible. If x approaching infinity, same thing, it approaches infinity. There's no bound in this. There's no ceiling. There's no floor. It goes up. It goes up slowly, but it still goes up forever. Obviously, it goes down very quickly. And then the graphs here should be pretty for y equals 2 to the x. That's pretty darn easy. Make that 1 and 2. But if I make each scale here 2 all the way to 10, for 10 to the x, it looks like this. So graph that and graph their respective inverses. So make a little table. This is not smart. I should move the screen. 0, 1, 1, 2. 0, 1, 1, 10. I kind of messed this one up. It's okay. I'll just do well, we know we're gonna have a point right here. You guys get the idea, right? It looks like that. Yeah. This right here?
Yeah.
Yes, that's equals 0.
Okay.
Yeah. Yeah, it's y equals 0 for exponential, x equals 0 for logarithmic. Now, of course, there's a transformation, which we'll talk about very shortly. Then you guys change that. If you do horizontal shifts, yeah, you got to change that. That has to happen 100%. We're okay with the graphs here. So I'll get. I'll just wait. Let's get caught up. Freeze that. So we'll generalize. We'll do some transformations, and then we'll stop there for today. Let me know if I can move on. Yeah. Okay. Cool. All right. So if we move on, the inverse obviously is x equals a to the y power, or y equals log base a of x. So again, my inverse is log base a of x. My domain here is all real for exponential, and 0 to infinity for the range for exponential. And it's just reverse for logs. So what would happen if a is between 0 and 1? Well, if you have y equals 1/2 to the x power, actually, hold on. Let me do the inverse. So if you do that, that gets a little weird. So if I plug in 1, 0, -1, it's going to look like this. 1/2, 1, and 2. So it'll look like that. And that's because if I were to reverse it, if I did 1/2 to the x,
On the answer by -1.
see how y equals x goes to the middle of that again? So that's what's happening for that one. The blue, by the way, is y equals 1/2 to the x. The red is the inverse. But that's all. I think it's all the same stuff, really. I mean, it's still a range of all real, but it kind of looks a little different. It's flipped in a way. So that's what we expect. Again, y equals log base a x is the same as x equals a to the y. That's the definition of log of a function. We keep a positive. A does not equal 1. Otherwise, you'd have just a linear function or a constant function. And x is greater than 0. We don't log negative numbers because you can't have a to the y equal x if a is positive. Yeah, I think that all makes sense. Okay. So any questions? No? All right. So let's do some transformations. I'll do probably the first couple. And let me look what the homework's like, because if the homework is kind of the same stuff, we could ignore page 13. What's the homework about? Yeah, let's just do page 12. I think we're good. You guys can have our homework because you guys get the idea. Okay, so we don't need to do page 13. We could forego that. Okay. All right, so let's do just a couple of these, and you guys can do the homework after that. So here's what I would do. I would do y equals log base 2x. So that's the same thing as saying what, guys? X equals what? 2 to the y. Let's make a table. Y is your input now. So we'll do 1, 0, -1. So you get 2, 1, and half. Now let's do my transformations. So I'm going to add what to X? I'm going to add what to Y? Good. So you have 5, 4, and 3.5. Yeah, you can draw clouds if you want. I don't care. If you want to be an artist, go for it. 2, 1, and 0. So 5, 2, 4, 1, 3.5, 0. And we expect to get closer and closer to what X value? Exactly, right? Because you can't log negative numbers. That makes sense, right? And generally, graph will take on this kind of a curvature. There you go. What's my domain? Infinity. What's my range? All real. And make sure you state the equation of the asymptote, which is X equals 3. Not that hard. I don't think we need to do this 5 times. That's crazy. We're not going to do page 13. Let's do B. Even though the transformations are pretty neat on page 13, just not worry about it. So go and try B on your own. You have to figure out what change happens to X, what change happens to Y, and do it. What's your base here, by the way? Yep. Your parent function is log base 10x. How are you going to change X, guys? Good. Sorry, divide by 5. And change Y by changing the sign. You guys get that? Yep. Okay, cool. All right, I think you guys can get started homework. We got about 15 minutes left. It's just going to be homework 9, the packet. Yeah, just work through it. Oh yeah, that's right. We gotta talk about it. Yeah, I don't want to think it's bad. I know you want to know what you I already know.
What?
Yeah, do it right now.
Bro cannot save.
Oh my.
Stop the recording.
I don't